Level 3 Temperature Instrumentation. This is part of the series on thermocouples. This is part 2, cold junction measuring and using thermocouple tables. Let's use some critical thinking. Tell me, what's wrong with this picture? Okay, the positive wire is on the positive terminal and the negative wire is on the negative terminal, so that's okay. As best we can tell, the meter is working and it's on the right setting. So what's wrong?
The answer? You cannot use your multimeter's copper leads to directly measure the thermocouple's Seebeck voltage. Why?
Well, the simple answer is you would create two new junctions, and they would develop their own Seebeck voltages. Okay, let's take a careful look at this circuit. So junction 1 is our intended measuring junction. Junctions 2 and 3 are supposed to be just connection points. However, they create their own Seebeck voltages, and those voltages oppose the thermocouple voltage.
Remember that two factors make thermocouples work: dissimilar metals and a difference in temperature. Your multimeter introduces a dissimilar metal. J2 is a thermocouple junction of iron and the copper from the multimeter lead. And J3 is a thermocouple of copper and constantan. If there's any difference in the temperature between these 2 points, you will end up with another thermocouple circuit, which, as we stated, opposes the original measuring junction voltage. Okay, so we took care of that with the isothermic block, right? Yes, but we're not controlling the temperature where the multimeter is, and that again creates a difference, and again we have a problem. So we must therefore stabilize the temperatures at J2 and J3 to a fixed known temperature before the J1 voltage and temperature can be properly measured. This is beginning to sound like an impossible task. I mean, how on earth do you get the temperature at the measuring junction if the voltage produced keeps changing every time you try to read it? Well, fortunately, the answer lies in something called the law of intermediate temperatures. For clarity, let's call our final metered junction the extension junction. The law of intermediate temperatures states that if a voltage is produced by the temperature difference between the measuring junction and the reference junction, and another voltage is developed because of the difference in temperature between the reference junction and the extension junction, then the total voltage produced is the sum of the two voltages created, and that the temperature at the extension junction determines the voltage, regardless of the intermediate or reference junction voltage. This also means we can use the reference junction at any fixed temperature as long as it is lower than the extension junction temperature. The beauty of this law's formula is that you can rearrange the formula to find the other components, as long as you know 2 of the 3.
Okay, let's set the temperature of the J2 and J3 junctions to a fixed value. First, we'll hermetically seal the junctions so there won't be any unintended temperature changes. Now, let's dump the whole thing into a nice tank full of freezing water. There, the junctions are set at 32 degrees Fahrenheit. And now, we can figure things out without worrying about J2 and J3's temperatures changing all the time.
So now we can calculate the temperature of the measuring junction. We'll begin by rearranging the formula so we can determine what we need to know. After all, our objective is to determine the correct voltage at the measuring junction and then convert that into a temperature. So the first thing we're going to do is we're going to take a reading at the extension junction. Let's say it was 1.9 millivolts. Remember, we can only take readings from the extension junction. Okay, So we plug 1.9 millivolts into our equation. Great. Now we have to measure the voltage at the reference junction. Oh, now that's going to be a problem, because now we have to somehow measure the voltage without a meter. Great. What is it going to be, a Houdini trick? Well, not a Houdini trick, a universal trick. Just like looking up the ampacity of a 4-rod aluminum wire. Like RTDs, thermocouples are manufactured to very specific standards. Every thermocouple type has a thermoelectric voltage chart that can be referenced for converting a measured millivolt reading into a temperature based on the 32 degrees Fahrenheit or 0 Celsius ice bath. The chart can also be used in reverse, as you can verify the accuracy of a thermocouple by checking the voltage against a known temperature. So we set the value of our reference junction to 32 degrees Fahrenheit. We now need only to look that up on our table to get the reference junction. We know that 0 Celsius is the same as 32 degrees Fahrenheit. So the chart is in Celsius, we're going to use that. Checking our table, we find under the 0 column and the 0 row, the voltage is, well, that makes life easy, it's 0 millivolts. Now is a good time to observe something about this table. Notice that the millivolt reading of 0 millivolts appears twice in our table. The blue circled one is in the 0 row, while the red circled one is under the 10 column. Well, that's weird. Okay. Each column is one higher than the one to its left. So if we follow back to the left, we find the red circled 0 occurs in the -10 row. Therefore, -10 adding 10 gives us 0.
To interpret the chart, start with the left-hand column. This chart, for example, tells you that the measurements are in Celsius. Notice that the temperature counts in tens for each row. Now notice that there are 10 columns. The columns count away from the left in increments by 1 degree. This means if you want 15 degrees, you find the 10 row and move over 5 to 15. 10 plus 5.
Let's practice. Let's look for 30 degrees. Okay, that's easy. It's in its own row under the 0 column. But it is also found on the 20 row in the 10th column. They are both 1.537 millivolts, which is perfect because 30 equals 20 plus 10. Okay, that's easy. Now let's look at the negative values.
Okay, let's continue practicing. This time, let's try and find the millivolt measurement for -18. Okay, so we take the negative row 20, we count up 8, and we get, oh, that's not right actually. That's -12. Okay, so we'll take the -10 row and count up 8, and that's, no, that's something that's not right there either. That's -2? It's confusing. I'll be the first to admit it. But when the values are negative, just remember this. Do the math to find your path. Now, -18 is greater than -10, negatively speaking. So the next row up is -20. Now, if we take the -20 and we subtract -18, that becomes +2. So this tells you to go to the -20 row and count over to the 2 column, and you get -0.896. We go over 2 because -20 plus 1 column would be -19, plus 2 would be -18. If you look at the values in the columns themselves, it's pretty easy. Above 0, the values increase as you go higher in a count, left to right. But on the negative side of the 0, the numbers decrease in negative value, which means they're going positive. You're actually still adding. In your class from the first week, you were given a bundle, and in that bundle was a complete J-type table. I would strongly recommend practicing this a few times, especially working with negative values. This is important to remember. It might be on a test, like your first job in instrumentation.
Okay, that was a lot of work to figure out negative voltages, but fortunately, we don't have to do that right now. Let's get back to the problem at hand. So we found that at 0 Celsius, the voltage was 0 millivolts. Let's plug that into our equation. We can now calculate the voltage of the measuring junction. The total is 1.9 millivolts, so our measuring voltage is 1.9 millivolts. With our final voltage determined, all we have to do now is to go back to the tables to determine what 1.9 millivolts tells us. Hunting down the 1.9, we find it under the 7 column and the 30 row. So 30 plus 7 gives us 37 degrees Celsius. This method of ice bathing the junction is called cold junction measuring. Here, cold means cold, as in freezing. Since all thermocouples use the freezing point of water to set their reference, you can always eliminate the reference voltage concerned if you lower the temperature of that junction to freezing. Let's work through an example. Here we have a very simple thermocouple circuit. Let's start by analyzing it. Which is the reference junction? If you guessed B, you're right. Which junction is the measuring junction? If you guessed A, you're right again. Junction C is what we were referring to as the extension junction.
Okay, so let's work through this. What is the measuring junction temperature if the junction voltage is 0.749 millivolts and the ambient temperature is -5 degrees Celsius? So here is the formula we need. The voltage at the measuring junction is equal to the extension junction's voltage less the reference junction voltage. Remember too that if you get a result that is negative here, then the measuring junction is colder than the reference junction. So what do we know so far? Well, we know the reference voltage is, so we'll plug that in. And now we're going to need to use the chart to determine the expected voltage for -5 degrees C. Okay, here we have a negative number, so we're speaking negatively. Let's remind ourselves that the first value in the 0 column on the left is the same value as the next row on the 10 column. Okay, so do the math, find the path. Great. Okay, now -5 is greater, again, negatively speaking, than 0, so we move up to the -10 row. Now we do our math. So if we take -10 and we subtract a -5, and the whole thing's in the negative, that comes out to +5. So we move to the right, or up to the 5 column, and the magic answer is -0.251 millivolts. So now all we have to do is plug in the missing numbers and calculate the measuring junction voltage. So 0.749 millivolts minus -0.251 millivolts, which means a negative times a negative is positive. So that gives us 0.749 plus 0.251, which equals 1 millivolt.
Now all we need to do is look up the temperature. 1 millivolt is between 9 or 10, but remember it's on the 10 row, so the temperature is between 19 or 20. So let's call it 19.5 degrees Celsius.